Okay, so we're going to begin these problems the same way we did the previous ones, where we're just going to pretend like this first one says y equals negative x squared, which is going to be an upside down parent function parabola. So we have 0, 0. Instead of 1, 1, it's 1, negative 1, 2, negative 4, etc. It is underlined, so my parabola is solid. All right. So we start by graphing the parabola like normal, and then we want to run a test point through this to see which region gets shaded. So are we going to shade the outside region, or are we going to shade the inside? So if you pick a point, say like 0, negative 1, all right, you're going to find out that that region works. So here's where it's a little different. I'm not going to shade this all the way because I have to remember I have to do another one of these, and there could be a lot of shading going on, and that means more erasing. So what I like to do is just draw arrows that indicate which region I would shade for that. When I go to graph the second one, same kind of thing. I'm going to go ahead and I'm going to graph the vertex. So h would be 0, which would mean k would be 3. So it's a little off the coordinate plane, but still doable. And then if you put just like 1 in for x, you're going to get 0. So then you just mirror that. So this is our second one. And of course it is dashed because it's not underlined. And then we run a test point through here. Let's say you want to try 0, 0. So 0 is greater than 3. That is not true. So we want to shade the side that's not including 0. So we want to shade outside of the black parabola, but inside of the red parabola. So again, I'm just drawing arrows. I'm not actually shading yet. I want to shade the region where the arrows are in agreement. So if you look right here, this region right here contains arrows of both colors, and so does this region. So that's the region that I'm going to shade. And then just, it's me being a neat freak, I like to hide, like erase my arrows when I'm done. So doing less drawing initially saves you on erasing at the end. So the solution regions are where the shaded regions are. All right, for letter D, again, I'm going to do red for the top one and black for the bottom. If I go ahead and compute my vertex, I'm going to find that h is negative 2.5 and k is negative 6.25, and that's for the first inequality. Now, since I have to get to 6, and they only gave me three sections down here, I'm going to count by 2s. That way I can fit my vertex on the coordinate plane. So right about here is where my vertex is. It doesn't need to be perfect, just somewhere close. So this should be close enough. And then if I pick another number and plug it in for x, say 1, I'm going to get 6. So then I'm going to graph 1, 6. And we have a solid parabola because it is inclusive. It's underlined. And if I run a test point through, let's say negative 2, 0, I find out that that does pass as the test point. So this is the region that I would shade. And then I'm going to do the black parabola. And this one's nice because it's already in vertex form. So my h is actually negative 2, and my k is negative 1. So I'm going to go ahead and plot that point. And then you can just pick a number to plug in for x. I chose 0, and 0 plus 2 squared minus 1 gets you 3. So I graph 0, 3, and then I did my best to mirror it. It, again, doesn't have to be perfect. And of course we want a solid parabola again. And if you run 0, 0 through this one, you'll find out that 0, 0 does not work. You'll get 0 is greater than or equal to 3, which is not true. So I would want to draw my arrows for the black parabola away from 0. So it looks like where these arrows agree, or where I see both colored arrows, would be this region right here. And so I'll just erase all those extra ones. So this region represents the solution region. Any point that's in here would satisfy both of these inequalities, and that's what our task is to do. And last but not least, I'll use purple this time. I like this parabola because it's basically vertically shifted up 2 and everything else is the same. So I just took a parent function and I made it go up 2. and 0, 0 would not pass this test, so I'm using 0, 0 as my test point. It failed, so I would want to shade the region that does not contain 0, 0. I also like this one because it's basically a parent function. It's flipped upside down and shifted up 1. So I can pretty much draw it like I would draw a parent with just those two modifications. And if I do run 0, 0 through this, I get 0 is less than 1. Now that is true, so I would want to shade the side that says 0, 0. So we have an issue here. I don't have any regions that contain both purple and green arrows. There's no regions that agree. So when this happens, we simply say there's no solution. There's not going to be an ordered pair that makes both of these parabolas true. There's not going to be an ordered pair that makes both inequalities true. So that's essentially how we treat these problems. It's not that they're really hard to do. You just have to take your time and not rush through them. So we don't usually get a lot of these problems to do because there is quite a bit of work that goes into them. But again, we just want to take our time, make sure we graph our first parabola correctly, we know to shade the correct side, we graph our second one correctly, we want to make sure we shade the correct side, and then we want to see if there's overlap. We're going to change gears and we're just going to do a couple word problems. So where on earth could we use our inequality rules to help us with word problems? So this is just a simple example. So we have a profit that's given by this formula. X stands for the number of hot dogs, Y stands for the profit. And I want to know, hey, what would X have to be so that you get at least $150,000? So the first thing that I'm going to do is take my formula. At least means greater or equal. So I'm going to take my formula and make it greater or equal to 150,000. Once you have that set up, you pretty much just follow your normal steps for one variable inequalities. We want to write it in standard form. So we're going to subtract the 150 over. And then we're going to jump right to the quadratic formula. This is going to be very messy, so we definitely want a calculator. So I just make sure I plug my values into the correct spots in the quadratic formula. And using my handy calculator, I find out that this nasty stuff inside all becomes 7,400. And then if I were to, type it in -140 minus root 7,400, and then divide that, and then do the plus version, these are the two answers I'm going to get. So these are your critical values, and they are rounded. I rounded to 2 decimal places just to kind of keep it accurate. Now we have to remember these aren't solutions, these are just critical values. We have to draw the number line. We have to put our critical values on the number line. And then we have to run some test points. So I would definitely run 0 for the first interval, maybe 2,000 for the middle one, and say 6,000 for the third interval. Again, pick whatever you want as long as they fit the criteria. That's all you need to do. And then we would substitute each of them into either the very beginning problem or our modified standard form version. It doesn't matter. Just to save on time, you're going to find the middle region is the only one that works. So typically what we do is we'd say, okay, so numbers between my first critical value and my second critical value would be the solutions to this inequality. The only catch is it's a word problem, so we want to make sure that our answer makes logical sense. Since X stands for the number of hot dogs, we can't really say, well, you need to sell or you need to produce more than 1,349.4 hot dogs. You're not going to produce 0.4 hot dogs. So the first number that is bigger than this number that makes logical sense would be 1350. So we have to make sure our answers make sense. And we have to have numbers that are less than this. Well, the first whole number that is less than this is 5650. So we would need to produce between 1350 and 5650 hot dogs to generate that profit. So just watch out for word problems. Make sure that, if decimal answers don't make sense, then you turn them into integer answers that do make sense. Last but not least, we're going to do kind of a substitution problem that deals with inequalities. These are quite popular. You'll find that as you take higher level math classes, they really like perimeter and area problems. So we're going to take the perimeter of a rectangle parking lot. We have to have the perimeter equal to 440 feet. We want our area to be at least 8,000 square feet. And then we want to just write an inequality to represent all the possible lengths of two of the sides. So step one is we're going to set up a perimeter equation. All right, and then we're going to choose, do you want to solve for L or W? It does not matter. You can find your W's or you can find your L's. They just want one or the other. So perimeter for a rectangle is twice length plus twice width equals perimeter. And I'm just going to solve for L just because. You can solve for W if you want. It really doesn't matter who you call length and who you call width in this problem. So I set up my perimeter equation and I solved for L. I subtracted 2W and then divided everything by 2. Step 2, now we're going to set up an area formula. So length times width gets you the area of a rectangle. At least means greater or equal to, and then 8,000. So we set up our perimeter equation, we solved for a variable, and then we set up our inequality. The reason we're doing this is so that we can substitute this answer for L into the area formula. So we're going to substitute, we're going to simplify, and then we're going to write our answer in standard form. So instead of L, I'm going to replace it with negative W plus 220. I'm still going to keep the times W from the area, and I still keep the 8,000 in the symbol. Do a little simplifying, and then change it over to standard form. So this is my new quadratic. And then the rest is kind of basically what we did in the previous problem. So we're going to set up our quadratic formula. And we're going to be very careful about the numbers we're substituting. And we absolutely need a calculator for this. So we'll clean it up a little bit. You get 16,400 as your new radicand. And then if you break it into two cases, you should get the numbers about 45.9 and 174.03. So again, that's all generated by a calculator. We're just shortening our time doing calculations since we've been doing that. And it is an inequality, so these are not solutions, these are critical values. We have to put them on a number line, and we have to test these three intervals. Now we've been testing intervals for a while, so I'm not going to run through all of that again, but I'm going to tell you the middle one is the one that you'll find that works. The other two do not work. So then what we just need to do is make a statement that our width is going to be between 45.9 and 174.03. And unlike the hot dog problem, these answers make total sense. You can absolutely have widths that are decimal units long. So that's not an issue at all. And once again, just to clarify, it does not matter if this is W or L. They just want to know, what are the possible lengths or the possible widths. That's really what they want to know. So obviously, if you have a certain width, you can then figure out what the corresponding length is and vice versa. So they do not care which one you call which. They just want to see if you can figure out the dimensions of one of the sides, the range of dimensions.